guys had a great time? It was okay. It looks like some people are still enjoying their break. Empty seats out there. Okay, so we're going to continue on lecture 21. We're also going to start chapter 13 now. So we're going to finish up chapter 12 and then get on with 13. So for a review for lecture 19, so we looked at sinusoidal positive feedback right here. And recall that for positive feedback, this right here is plus. But what happens is that when you look at the gain of the entire system, you have a minus here instead of plus for the positive feedback. And for the Barkhausen criteria, which we'll talk about again today, you want the angle of your loop gain to be 0, and you want your magnitude of your loop gain to be 1. That forces this denominator to be 0 if that's 1, because it'll be 1 minus 1. We also looked at the Wien-Bridge oscillator right here. And we looked at its loop gain right there. And we also looked at the phase shift oscillator. And for that loop gain, instead of having it be 0, the same thing is if you have it go to 360, same thing as going to 0. And those are two types we looked at. And we looked at the conditions that are required for the Barkhausen criteria for oscillation. For lecture 20, right before break, we reviewed the diode right here. And then we looked at this precision half-wave rectifier, which is a whole lot better than this diode right here. So you want the behavior of a diode, but you want to improve it, so you couple it with this op amp right here. And so you have a much better behavior. But the problem is with this is that you have this saturation effect, where when it's saturated, when the difference here is negative, what happens, it takes a while for the circuits to recover from that. And so to prevent that from going full saturation, you can use a non-saturating precision rectifier. It has a behavior like this, but it has the characteristic that you want, where it's pretty much 0 here, then it turns on. You get that by using some more feedback right here and 2 diodes instead of 1 diode. Okay, so that's for the non-saturating precision rectifier. And of course, the issue with comparators that we saw were that for noisy systems, you can have this switching that goes back and forth between the 2 saturation states, and you don't want that. So a good way to deal with that is to use the Schmidt trigger right here. And so it actually takes this piece right here and it widens it up, right? So now you have this hysteretic effect right here. So what happens is that even though the output will go to its saturation states of VCC and VEE, what happens is that as soon as it goes to a saturation state, it then changes what your reference is from beta VCC to beta VEE. So that switches as these 2 switches. And because that switches, this input has to now either climb way over here to switch or climb way back over here to switch. And so that avoids the noise problem that you get right here, where you could just have a small little shift here to cause you to go up here or down there. Okay, so that's the Schmidt trigger. Yeah. Oh, this beta comes up a lot right here. So this beta right here, we're going to see a lot today. This is R1 over R2 plus R1. Okay, so that comes up a lot. So just keep in mind what that is. Okay, and that's for the non-inverting op amp. That's where that came from. Okay, so concepts for today continue with the positive feedback. Then also we get in chapter 13 with using the transistor like the BJT and also the MOSFET as an amplifier. Okay, so continue on with these types of systems using comparators. Let's look at the astable multivibrator. Okay, now this has no stable state. That's why it's called the astable multivibrator. So it employs a combination of positive and negative feedback to generate a rectangular output waveform. So this is the output right here of that node. It's a nice rectangular waveform that you got out of it. Okay, and it just periodically switches between these states. So up here, you get the VCC from here, and then down here, it saturates to the VEE down there. Okay, just flips back and forth. So we're going to analyze to see how that actually works. Okay, so so if the output has just switched to VCC at t equals 0, and we'll keep resetting the time to t equals 0 at every state. But let's say you're right here, and then and it just switched the output to this VCC. Then what happens? Then the voltage at this inverting node, which is also the voltage across this capacitor right here, it starts charging exponentially from this beta VEE toward the final value of VCC. Okay, so that's what's happening here. So before it switched, like if you're over here, before it starts switching right there, this voltage was down here at beta VEE. And that's from up here, right? So remember, this is the beta right here, which is R1 divided by R1 plus R2. Okay, so beta, and then it was at VEE, was saturated at VEE over here before it got to 0. Okay, so that's why it's beta VEE. So that's the voltage across the capacitor. So you're down here, then as soon as you switch to VCC, that's going to be VCC right here, and then this charge right here is going to start climbing from this negative beta VEE toward VCC. It's going to asymptote to that value. Okay, so that's what happens. And it does so at a time constant of tau equals RC. So this is the time constant. And that's how you can actually adjust your period of change, right? Before it starts switching and going the other direction. Okay, so as soon as this this inverting node voltage exceeds this voltage right here, remember this, if that's VCC at that point, then this voltage right here is beta VCC. So as soon as this voltage climbs up and it exceeds this beta VCC voltage, then it switches the other direction down to here. Okay, so once it exceeds that, then it switches to the output switches to VEE. Okay, and this keeps on going back, right? So first the capacitor's down here, it goes up until it reaches the voltage of your reference right there, which is sitting at beta VCC. Once it does that, then it switches down to here, and then it's going to the voltage across the capacitor is going to try to drain out and asymptotically try to reach this negative VEE. Of course, it never gets there, because then what happens if that's VEE now, then the next switching happens at beta VEE, which is down here. So it just keeps on switching back and forth like that. So this is what's happening across the capacitor, but this is what's happening at the output. Okay? So again, the output is due to the comparator, which is just doing a strong shift from VCC to VEE, like that. But inside of here, because of the time constant, it takes time for this capacitor to charge up and decay to its resting, to its stable asymptotic states. But it tries to get to VCC and VEE, but it never really gets there because it switches because of that reference voltage right there. And that right there keeps switching too. Okay, so any questions about how this works? Right here? Okay, so, so let's look at the mathematics behind this. So this is what happens with the voltage across the charged capacitor. Okay, so right here, the voltage is charging and it's trying to get to VCC. So the equation looks like this. So here's the voltage across the capacitor, this VC, okay? And actually, you could look at this equation. Okay, so you know it's going to have this kind of character, right? It's going to be an exponential type of increase, or in this case, exponential decrease, right? But it's going to be this t over tau, okay? Now, you want to get the asymptotic values right? So when t is 0, at that point right there, then this expression right here is exponential to raise to the power, e to the raise to the power of 0, so that's going to be 1. So what you have is VCC minus VCC, so those cancel out, and all you have left is a minus beta VE, okay? And that makes sense because you're starting off at beta VE. So that's one extreme. The other extreme is when t goes to infinity. Ignore the switching part, right? Just assume that it finally gets there to infinity. So when this is infinity, it's going to be e to the negative infinity, right? So that's going to be 0, and so that means this bracketed expression is going to cancel out. So it's going to be VCC minus 0. So the ending value is VCC. So those are your two extreme values, right? And for your intermediate values, then is when this t is not 0 or infinity, and then that's how you get your other intermediate values. And you just know it's going to be exponential because you know how the behavior of these RC circuits go. Okay, they're first order differential equations, and they have this type of exponential character. Okay, so now what about the time for the voltage for the switching to occur? Okay, so you know what happens. So this equation, it really doesn't get to a final value of VCC, right? It switches at this point and doesn't go on. So the question is how do you find this time from here to here? Okay, so it's the same equation, except that at this time right here, you know where your voltage VC is going to be. You know that VC voltage across the capacitor is going to be beta VCC, right? So here's VCC, where it's got to its saturated value. This point right here is beta VCC, and so that's where the crossing point is for switching. So that's going to be your final value. And it's not just any t that happens at, it happens at t1, your period for it to get from here to here, that time. So plug that in as final value, right? And solve for t1, and then you get this expression. So this right here is the time it takes to get from t equals 0 to right here.
So beta always going to be between 0 and 1?
Yeah, for this kind of system it is, because it's just this ratio. Well, let me take that back. Sometimes you can have a beta like this, because I've seen that, where let's just say that you may have some type of impedance here, some type of impedance here, right? You call this, the feedback one, and that's that one right there. And then in that case, that beta is going to be this ZF over ZF plus Z1. In this case, they're both resistors, right? So you don't have to worry about that. Okay, it's going to be that fraction. But you may have something else here, and then you just look at it as in terms of impedance. Okay, so it may be a little more complicated. It may be frequency dependent. Yeah. Oh, and of course, that beta was found by voltage division, right? You have no current going off that direction, right? So what you're doing is just using voltage division, saying, well, is this impedance that's left to ground divided by the total impedance, multiply it by where your voltage is starting from. That's where this beta came from, right? Where you're having that voltage at the yeah, the inverting node equals VF over CF plus V1 times V out. Just voltage division. Okay. Yeah, but remember that was really necessary when we did that comparator to get rid of the noise, where this situation was used to separate that from being at a value that's really close to your input value. So you have that hysteresis going on. Okay, so so for T2, the next time, right? They may not be equal. Okay, I mean, you don't have to have them to be equal, right? So now your voltage across your capacitor is now discharging, right? You got up to this value right here. Now you switched, and instead of being VCC right here, it now saturated to VEE. If that's VEE and that's your output voltage, then this voltage right here is beta VEE, or negative beta VEE. So that's the next switching part right here. So the question is what is the time that goes from here down to here? Okay, and that's what this is about right here. Okay, so if you look at your asymptotic values, now remember this is time shifted. Okay, so that's why you don't see something in there like T minus T1. They time shifted it, so now that's now T equals 0, and this is your next time, okay? So they're just calling it T prime. So it's really not this axis. It's like a T prime where this whole thing is shifted over to here, okay? But let's look at the asymptotic values. So when that's 0, this becomes 1. So that minus VE plus that goes away. And so your initial value is just beta VCC. And that's right. You're starting from that right here. When T prime is 0, you're at beta VCC. Then as T prime goes to infinity, exponential of some argument going to negative infinity, that's going to be 0, right? So then your final value is negative VEE, and that eventually, as time T prime goes to infinity, eventually gets to negative VEE. Okay, so that's this right here. And then all your intermediate values are just for T prime. So that equation works. Again, you could do it by doing your first order differential equation, right? And you could do it by doing your time shift, like you learned in 2100. I mean 2120, I think. Or you could just do it this way and work, right? And then determine your initial and final values. and I'll do it. And notice the difference between this right here. See right here? This was VCC minus those two things. This right here is negative VE plus those two things. Okay? And that's for this climbing up exponentially, and this is for it decaying exponentially. Okay? So, anyway, so to solve for T2, this value, and remember T2 is not from this value all the way to here. T2 is just from here to here. That's what T2 is. Okay? So to solve for T2, you put in the final value of that, which is negative beta VEE, which is right here. And then you make that T prime, make that just T2, right? And then you solve for T2, and then that's what you get right here. So that's T2. So T1 is this period from here to here. T2 is this from here to here. Now, I was calling those periods, but I shouldn't have, because a part, the period is when the whole thing repeats, right? So the whole thing repeats after it goes from, it does a T1 and a T2. Then it repeats. So that's the period, right? Okay, so so here you just add them up. So this is the total period right here, T1 plus T2. If you add it up, add this piece plus this piece right here, then you get that. Okay, and that's the period of the whole thing. And again, if you want this to be more of like a triangle type of thing, you can change your exponential decay. You play around with your values. You can get your T1 to behave more like T2. So these are identical or nearly the same. So you can play around with that to change the shape of this. But that's the astable multivibrator. Okay, so now this is the monostable multivibrator. It's also called the one-shot. Well, it's not only called the one-shot. It's also called the monostable circuit or the single shot. So there's several names. But it does exactly what it's what it sounds like. It's like one pulse, right, for a certain T1. Okay, so so this monostable multivibrator or one shot, it operates with one stable state. Okay, so remember these are the reason why this was called astable is because these are really called when this is just charging up like this. If it didn't switch, it would keep on going, right? And so that's where they're calling this astable, right? So it's kind of stable because it stays in this range right here, but then it's unstable because its instability is the thing that keeps it going, okay? However, this right here, it could stay at a stable state for a long time until you trigger it. Once you trigger it, then it does this thing, but then eventually returns to its stable state. Okay, so this is used to generate a single pulse of a known duration after it sees a trigger signal. So the circuit rests quiescently in a stable state until triggered, until an unstable state, but it returns to a stable state after some duration t. And you can see the difference too. You see the diodes right here? Like if you look at the last one, there's no diode right here, right? And also, there's a diode added right here at this node. Okay, so that resistor R1 is this one right here. So they stuck it in diode right here, stuck it in diode right here, but left everything else the same. See that? Okay, so this is what it looks like for each part. So here's like the trigger input. So it's like just a little pulse comes in here, right, to turn this one on, and momentarily makes it a forward bias. So current can go in this direction. Once current starts going in here, then you've turned it on, because then this voltage right here then changes, and then that's going to change its stable state that it used to rest at to now start to charge up that capacitor. Okay, and here's what's happening when it's charging up the capacitor. It's this mono unstable state right here. Okay, but once it gets to the switching part, just like last time, then it switches like this, and then it gets stable again, and it stays. There's no other switching that happens. And the reason it doesn't switch is because the diodes. The diodes keep it from switching back, continuously. So here's the output. It just goes for a particular duration. This duration right here is independent of this. Okay. Well, I think this needs to be shorter than that. But once you put it in a quick pulse right here, then it'll go for this amount t right here until this charges up enough, and then it goes back to this, and it stays there indefinitely until it receives another pulse of input. Okay, so here's what's happening at a stable state. So at a stable state right here, the output rests at V out equals negative VE. That's when it's down here. This is stable. It's the state right here. So it's resting at negative VE. VEE. Okay. And so this input right here, this VT right here, this is less than the voltage right here. So we know this voltage right here. This voltage right here is just beta, whatever that is. So this is the beta, and that's of, you know, the is resting at VEE or negative VE. So that's what that is, and that's just equal to negative beta VEE. Okay. So that's when it's in the stable state, and it stays there. Okay. So that means that the diode D1 right here is off. That means that this voltage is higher than that voltage, right? So it's off. D2 is on, okay? That means that even though this is ground, yeah, for this to be on, is this voltage right here higher than 0 or lower than 0? Yeah, exactly. Because for it to be forward biased, this voltage has to be higher than this voltage. And it is if that's going to be negative, because that's 0. So that's on, right? And, you know, C is going to discharge until it gets down to a particular value. Typically, you have this voltage across here, this diode voltage of VD. And so if you're right here and you go downhill VD, then that means this point right here is negative VD, right? That's what this line is, okay? So that's 0. Right here is down VD from that. So negative VD is this value right there. Okay. So, so for the comparator input, the VID right here, the input right here, the difference, the differential input right here, it is this value right there, which is the negative beta VEE, which we talked about before. That's that voltage, minus this voltage. This voltage right here is at negative VD. That's this voltage right here. Okay, so here's the voltage. And so the condition for stability is just looking at that. This VID, it needs to be negative, or this beta VEE, it needs to be greater than that. So if this value right here is greater than that, and since that's negative, then that means this sum is going to be negative, which means that that is going to be that's going to be negative. And so that's the necessary condition for stability. Okay. For the unstable state, what happens when you receive a pulse that comes in, right? That VT right there then becomes greater than this voltage. So this voltage right here is greater than this voltage, and we know what this voltage is. It's beta of that VEE. Then your D1 turns on, and that causes this voltage to be greater than this one. So when this turns on, then this voltage becomes greater than this voltage, which causes your V output to then switch. It's a comparator, so it's going to switch from this up to that. And then your voltage right here begins to rise up to beta VCC, because remember, we were sitting at beta VEE down here, then it switches to this. So that means now it's going to rise up to beta VCC as it switches from here to here. Okay, so the capacitance rises. It was sitting at negative VD, negative VD. It's going to try to rise up to VCC, and this is what happens. Again, here's the exponential part of that, and we talked about how this kind of thing behaves. Okay. And so once this voltage across the capacitor reaches this beta VCC, then the state changes back, and then in that time duration for the pulse right here, down to there, is you just plug in your final value, and you solve for t, and that's this right here. And that's the time it takes it to get back. And like I said before, this, if you look at all the terms here, is independent of that time, right? So extend an incoming pulse to get it started. It's just a pulse that causes it to switch from here to here, okay? Okay, so let's try to, oh wait, any questions about the monostable before we go in? I don't know then. That's a good question. There's probably a minimum, right, for this to get started. It maybe has to do with I guess we have to do with what is the time or the amount of input necessary for this to switch. How like for that to sense something coming through there to switch. That's what I'm guessing, but I don't know. Okay, so let's look at this example of making a really inexpensive analog function generator. Okay. So we looked at these components before. We just seen the astable multivibrator, right? We also know what the integrator does, and we know what the low-pass filter does. Okay. So what you can do is chain these things up together, and then at each point, you know, pick off the kind of signal that you want. You know, this right here can give you a square wave output. Okay, because we just saw that, right? Now, if that's not what you want from your output of your waveform generator, then you say, well, let me continue it on through here. Well, this right here is an integrator, and so if you're going to integrate a rectangular pulse, that's just a ramp, right? If you integrate it in time. Well, that's what this is. So this is a triangle wave output is going to come out of this. Okay? And if you take that triangle output and then you put it through a low pass filter, then you're going to get something that's like a sine wave. I'm not sure it's going to be exactly a sine wave, but it's going to be something that looks like a sine wave. Because it's going to round those sharp turns, right? So that's what this does. And look at the difference between the two. You know, this is the integrator. If this capacitor was, if these two things were switched, that would be a differentiator, right? But if it's on the feedback, that's the integrator. And if you make a leaky integrator, then that's like a low-pass filter, okay? And that's the astable vibrator. Now, if you want to adjust things, because remember, your multivibrator, that's the thing that's setting up your oscillation, right? And to tune your oscillation, remember, we saw for t, time. So to tune your oscillation, you could use, you could tune this resistor or tune that capacitor. To tune the resistor, you can use a potentiometer, right? You could twist your potentiometer around, and that would be a continuous change in frequency, you know, all of your period t's right there. This is, I mean, yes, you can tune a capacitor by changing the plate distance, right? But typically, how this is done is that they'll have several other capacitors that you just switch to, right? So you just like switch to different decades of capacitors, right? That are different by order of magnitude, right? So you switch to a certain order of magnitude, and then any intermediate value, you use your potentiometer to fine-tune the kind of frequency you want. So that's that. So now you know how to make a function generator. Questions? Okay, chapter 13. Okay, so for chapter 13, here are kind of things that this chapter covers. It starts using transistors as linear amplifiers. And so we've studied amplifiers a lot, and we know how they behave. But op amps aren't the only kind of, you know, amplifiers. You could use transistors if you get it to the right region, okay? And we'll also look at DC and AC equivalent circuits of these transistors, okay? Because that's a good way to analyze them. And then we'll use coupling on bypass capacitors and inductors to modify the DC and AC equivalent circuits. We'll look at the concept of small signal voltages and currents, small signal models for diodes and transistors, identification of common emitter, common source amplifiers, amplifier characteristics including voltage gain, input resistance, output resistance, and linear signal, and this rule of thumb estimates for voltage gain for common mode and common source amplifiers. Okay. So, so let's look at BJT first as a linear amplifier. Then we'll go to MOSFET. So, have you guys dealt with BJTs before, like in the previous class? Okay, good. All right, so so BJT is a bipolar junction transistor, right? But you can use it as a linear amplifier. So this is it right here, right? The BJT. Okay, so what you must do is provide a bias to the transistor in order to stabilize it at this operating point called the Q point. That's this right here. Okay, so you see these curves, right? They have these different values, but there is a certain sweet spot where you can use it as a quite linear amplifier. And so once the DC operating point has been established, then you can use the transistor as an amplifier. But of course, you have to make sure that your signal, and that's why they're calling it small signal, that the amplitude isn't too large. Okay, so there's a range that you have to deal with. Okay, so to go over this right here, you can see here you have a DC component and an AC component. And both of these together is the signal that's coming through right here. Your DC component is used to get the Q point that you're looking for. And here you can see you have your input signal coming in here. Here's the middle line right here. This goes up here. Here's the peak right here, which goes to this peak. And here's the lower peak, which goes to this peak. So sort of like what we've seen before with the op amps. Okay, but you have this this base emitter voltage right here, which is 0.7 for the input. That's what that is for typical Q point right here. It has a peak to peak or amplitude value that you have to worry about, and that's for the AC component. Okay. Oh, and I forgot to say, this axis right here is the collector emitter voltage, right here. The voltage between here and here, collector emitter voltage. And this axis right here is the collector current, right here, passing through. Okay, so the base emitter voltage is from here to here. So that's like from ground to right here. So this base emitter voltage is basically the sum of this and this. That's what this is right here. Okay. You also have this collector voltage, which is the load line, and you could get that by KVL right here. And this line right here is just like the straight line equation, right? So let's see, the output. I mean, your output is collector current. So if you put that, like if you solve for that right there, you have your IC that is equal to 10 over R C plus this C over R. Okay, so if you think about it, it's sort of like this. It's like, well, let me put that on the front. This is like y equals mx plus b. So here's like your y-intercept right here. And if you did like 10 divided by RC, in this case, your RC is 3.3 kiloohms. 10 divided by that should get you something around here, which is at 3. So this line right here it has a negative slope. The slope is 1 over RC. Okay, it hits it right here about 3 milliamps. That's what this value should be, right there. Okay, so that's how you get this load line. And for the gain, it's a little different. Okay, you're going to do it in terms of phasors. Okay, so that's why this collector emitter voltage right here is 1.65, right? So if you look at the collector emitter voltage, 1.65 is like, I mean, it's sort of like ignoring this average value and it's just looking at the amplitude of the oscillation. And it's 180 degrees because you can see that here, right? When this is going up right here, this is going down. Or you can see it here too. As this is going up right here, that's going down, right? So they're 180 degrees out of phase, which just means it's negative, right? So that's what that's for. That's 0.008 millivolts, and that's right here from 0.700 to 0.708 and down to 0.692. So this is like the amplitude right here. And so doing that, these angles, this minus 180 minus the denominator, 180, right? And then you could just say that that's just negative 206. Okay. Now here's for the this is for the MOSFET. Okay, so MOSFET, metal oxide semiconductor field effect transistor, and using that as a linear amplifier. It's pretty much the same. Here's the load line right here. The voltage right here. You have a DC component, which gets you your Q point right here. Okay. Here's your AC right there. And so here's the same kind of equation to generate this line right here. And here's the gain. You have your drain source, 4.13. So for this right here, it looks like they're using peak to peak, right? Because 4.13, to go from 2.7 to 6.7, that's like 4. Okay? So as long as, I mean, if you're going to do peak to peak here, you got to do peak to peak there. And so that's 1, and clearly they're doing peak to peak here. Same ratio. So you use amplitude or peak to peak. It's not that big of a deal. Again, 180 over 0, because as this increases, that is decreasing. As that increases, then that is decreasing. Okay, so that's what that is. And you can see a big difference between the two, where if you look at this amplification right here, that gain and this gain, that's like negative 206. This one is negative 4. So big difference between the two. And there's going to be other differences too that we'll look at. Yeah, so here are these two be, in comparison together. You can see what they look like. Okay. So any questions about the MOSFET or BJT? Yes. Oh, yeah. So these Q points, from what I gather from the book, these right here is likely different for what you get. So the manufacturer would tell you where the Q point is. But once you're around that Q point, which could be slightly different for, depending on what type of transistor you get, then you're able to do your oscillation. But then it puts a limit. I mean, you can see here, this one right here is almost at the limit before it starts changing, right? So you want to be careful about that, but yeah.
It's a little over 4 on the graph.
Um,
And is its value like significant at all, where it lines up on the x-axis?
yeah, I do see that. That's interesting. Let's look at the. Oh, okay. So, yeah, yeah. This right here is the drain source voltage right here. Um, yeah, yeah. So this drain source voltage right here, that Q point is like around 4.5, but this coming in right here, this right here is at the 3.5 coming in right here. So whatever that Q point is, yeah. These values do not line up with these values or these values. So it's a kind of a strange plot. Yeah, but I can see the confusion right here. So it's like you have these other plots thrown in on top of these other plots with these other axes. Okay. But if you know where your Q point is, you'll set your that value at your 3.5 line, and then you go up and down your peak values right here. Then you're able to get some kind of picture of your output. Yeah. Good. Yeah, but good question though. So anything else? Okay, that's it for today. See you guys on Wednesday.